Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will drift into the gentle mystery of quantum entanglement, a phenomenon so delicate and so strange that even the greatest scientific minds once hesitated to believe it. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, feel free to leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's always a small joy to imagine all the places we gather from, each person wrapped in their own little corner of the night. Now, if the lights are dim, your pillow's comfortable, and your breathing beginning to slow, let us gently open the door to a universe filled with quiet connections. And if your mind begins to wander along the way, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine, for a moment, that the universe around you is resting. The walls of your room are still, the night feels calm, and every distant sound has softened to a faint whisper. In this hush, it becomes easier to sense something deeper. The idea that beneath all this quietness, the universe itself might be quietly connected in ways we don't usually see. This is where our journey begins, not with heavy equations or spinning particles drawn in textbooks, but with a feeling, a soft sense that the cosmos might hold tiny threads between its smallest pieces, threads so subtle that only when we look closely do we notice how extraordinary they are. Physicists once thought the universe was a place of very clean separations. If two things were far apart, they stayed far apart, not only in space but in influence. A planet cannot tug on a pebble light years away. A candle flickering in your room cannot disturb a star on the far side of the galaxy. Distance meant something firm, something absolute. Yet, as the science of the microscopic world slowly unfolded, this old certainty began to soften. The deeper researchers looked into the tiniest building blocks of matter, the particles that dance invisibly beneath everything we touch. The more they began to notice strange hints that separation might not be as simple as it seems. This is where quantum entanglement quietly steps into the story. And to keep things soft and sleep-friendly, imagine this not as a complicated physics term, but as a kind of secret partnership between particles. When two particles become entangled, they share a connection that doesn't fade with space. You can carry one to the other side of a mountain or even a galaxy, and the connection remains, not as a line or a signal, but as something woven into the way the universe lets these particles exist. You might picture two fireflies resting inside a glass jar. When the jar is shaken softly, the glow of the fireflies flickers together. Now imagine opening the jar and letting one firefly drift on a breeze to a distant field, while the other stays in your hand. In ordinary life, the two should now have nothing left in common. But imagine instead that no matter where they wander, if one firefly flickers, the other flickers too, not because one sends a message or because light races between them, but because somewhere deeper, their glow was written as a shared story from the beginning. This, in spirit, is what entanglement tries to tell us. Two particles, once prepared in a certain way, behave as if they share a single, quiet script. They don't communicate, they don't exchange signals. Instead, the universe simply treats them as parts of one joined pattern. And when someone, a scientist or an experiment, or even just a curious observer, finally measures one of those particles, forcing it to reveal something definite about itself, the other particle instantly falls into place within the same story. It is natural to ask if this means information leaps faster than light, but the answer is gentler and more subtle. Nothing travels, nothing is sent. It is more like turning a page of a book. The words on that page do not take a journey to arrive where you see them. They were already written there, waiting. The act of reading simply reveals them. In the earliest days of studying this phenomenon, even Albert Einstein found it unsettling. He called it a spooky action at a distance, as if two distant things somehow whispered to each other in ways that defied common sense. And yet, decades of experiments have shown that the effect is real. The universe allows this soft, mysterious linkage between particles, even across vast distances. But tonight, we won't rush into the mathematics that normally accompanies this topic. If there were formulas, symbols like the Greek letter psi for the wave pattern of a particle, or the absolute value bars often used to write down the states inside a quantum system, we would translate all of them into quiet images instead. So instead of psi, imagine simply a gentle ripple. Instead of symbols that describe superpositions, think of a coin spinning in mid-air. Not yet heads, not yet tails, but momentarily something in between. Quantum mechanics often uses symbols to capture these ideas, but your mind can hold them without any of those characters, simply as stories. As you drift deeper into this thought, try imagining that everything around you, your room, the sky outside, the faraway stars, sits upon a tapestry woven from countless tiny threads. Most of these threads are ordinary and predictable. They respond to pushes and pulls, to forces and fields. But some threads weave sideways through the fabric in ways that are invisible unless we look with great care. Entanglement is one of those threads. Quiet, strange, and beautiful. The comforting part is that you don't need to hold the full scientific picture all at once. You only need to hold the idea that the universe is not built from isolated pieces. Instead, it behaves more like a great, delicate pattern, where distant points sometimes share gentle coordination. A kind of cosmic harmony that's easy to miss but surprisingly calming to consider. As we go deeper on this journey, we'll uncover why this strange connection puzzled Einstein, how it was tested experimentally, how some physicists believe it may tie into multiverse ideas, and what it might mean for our understanding of reality. But for now, let your mind picture two tiny particles floating in a sea of darkness, glowing faintly with a bond they never lost. Wherever they go, whatever paths they take, the story between them remains, and in that quiet image lies the beginning of everything else we're about to explore. When you first hear the phrase quantum entanglement, it can sound like a complicated knot of ideas, as if you're being asked to solve a puzzle full of symbols and rules you've never seen before. But tonight, we'll take a different approach. We'll unfold the idea slowly, like smoothing out a soft sheet, letting the wrinkles relax one by one. No equations, no intimidating diagrams, just gentle images that help you feel the shape of the concept, rather than wrestle with the formal definitions. Imagine holding a pair of tiny glowing beads in your hands. They start very close together, close enough that they sense each other, almost like two raindrops touching before they fall from a leaf. When they are prepared in a certain way, a way scientists do with careful arrangements of lasers, crystals, or trapped atoms, the beads become linked, not physically, but in terms of their possible behaviours. They become entangled. After that, you could place one bead in your pocket and toss the other across a wide, dark field, and the link still remains. Whatever happens when you examine one bead will be reflected in the behaviour of its partner. It's as if they still share a quiet understanding written into their very existence. To make this gentler, think of a coin spinning in the air. While it's spinning, before you catch it, it's not yet heads and not yet tails. It's living in a kind of soft uncertainty, a mixture of both possibilities. In quantum physics, this blurred state is often written with a symbol that looks like a curvy line, representing the wave-like nature of a particle. Instead of using that symbol tonight, let's imagine the spinning coin as a faint shimmer that holds more than one future at once. Now, suppose you prepare two coins in such a way that their fates are linked, not because one is secretly marked or because they're connected by strings, but because their shimmering spinning possibilities have been woven together. If one coin eventually shows heads, the other must show tails, and if one shows tails, the other must show heads. Before they are actually checked, both coins are in that soft, shimmering state. They are undefined individually, but perfectly coordinated as a pair. This is entanglement in its quietest, simplest form. Two objects that don't have individual stories until they're observed, only a shared story. It's important to understand that before the moment of measurement, neither particle has a definite property the way we normally imagine. It's not like two sealed envelopes, each containing a predetermined answer. Instead, it's more like two blank pages that will reveal matching patterns the moment the first one is written on. The second page, no matter how far away, instantly receives the corresponding words, not through a signal travelling across the room or across the galaxy, but simply because the story always belonged to both of them. This is where many people ask, does this mean the particles communicate? The answer is softer. It's not communication. Nothing travels. It is more like turning on one lamp, and in another, distant room, another lamp glows at the same instant. Not because electricity flowed, but because they were wired together at the deepest level from the start. The universe is simply revealing a relationship that already existed. To keep this soothing and sleep-friendly, imagine two dancers who begin a performance back-to-back. They rehearse a routine that requires perfect coordination, each gesture matched with a complementary gesture. Then the stage is split in two, and each dancer performs in a different room. When someone peeks into one room and sees a dancer raise their left hand, they instantly know the dancer in the other room has raised their right. Not because the dancers sent messages or checked their positions, but because the choreography was shared from the beginning. Another helpful picture is this. Think of two bells cast from the same mould. If you strike one bell, it rings with a certain tone. Now imagine that simply observing the tone of the bell in your hands immediately tells you the tone of the bell miles away. You didn't send the sound across the city. The two bells were shaped together, and their resonance is part of a single shared pattern. Nothing moves between them. You're simply uncovering a harmony that was already present but hidden. At this point in most physics discussions, you would see mathematical expressions written in tall vertical lines, symbols representing states or possibilities. They might have arrows or absolute value bars which look like two straight lines. But since we want this journey to stay gentle, we'll translate all that into simple language. The mathematical symbols are just ways to describe how deeply two objects can share information without exchanging it. Think of it like a pair of musical notes played together. You don't need to write the notes on a staff to hear the harmony. You can simply listen. Entanglement tells us something very quietly profound about the universe, that separateness may not be absolute, that things which appear far apart can, in a deeper layer of reality, remain part of one pattern. It doesn't mean spooky signals race through space. It doesn't mean we can whisper across galaxies. It simply means that the universe sometimes writes its stories in pairs. And perhaps the most surprising part is this. It happens all the time, in laboratories, in crystals, in beams of light split by delicate equipment. Entanglement is not rare. It's not exotic. It is woven into the world around us. We simply don't notice it because its effects hide under the veil of everyday experience. As you rest here, listening softly, imagine again those two faintly glowing beads drifting away from each other across an otherwise silent universe. They carry no wires, no radio waves, no hidden maps. Instead, they share a bond written so quietly into nature that it remained a mystery for decades. And yet, once you begin to see it, it feels almost peaceful. A reminder that even in vast distances, even in the deep cold of space, something in the universe likes to keep tiny pieces of itself gently, mysteriously connected. If you close your eyes for a moment and imagine the universe not as empty space, but as something textured, something with depth and softness, the idea of entanglement becomes easier to hold. Instead of picturing particles as tiny dots floating in a void, Imagine them resting on a vast, delicate fabric. This fabric stretches in every direction, farther than your mind can wander, and each point on it is connected to countless others through threads too fine to see. These threads don't tug or snap like ordinary strings. They shimmer gently with the possibilities that quantum physics talks about. And some threads, the entangled ones, shimmer in unison no matter how far apart their endpoints drift. This image is easier to grasp than the formal symbols scientists use. In textbooks, the relationship between entangled particles might be written as a mathematical expression inside vertical bars, or as a combination of two possible states glued together. But instead of imagining those symbols, imagine something softer, two ripples appearing on the same pond. When one ripple changes, the pattern of the other changes too, not because water flows between them, but because both ripples belong to the same surface. They are part of one body, one quiet shape. Entanglement is like that. It is not a message sent from one particle to another. It is a shared texture of the universe's fabric, a single pattern expressed in two distant places. When we measure one particle and force it to reveal one of its possible natures, we disturb the fabric in a way that makes the other particle fall into place within the same pattern. The universe isn't sending a note across space. It's simply showing you that both particles were written into one story. To make this even gentler, picture a wide, handmade quilt. Across its surface are intricate knots, small places where threads cross and tie together. Each knot connects patches that might be far apart on the surface. If you gently pull on one patch of the quilt, a patch on the opposite side might shift, not because anything travelled between them at that moment, but because the threads connecting them were sewn long ago. Entanglement is a connection like that, sewn before the particles separate, quiet but deeply significant. Another comforting picture is to think of entanglement as a pair of lanterns placed on opposite hillsides. If someone shields one lantern and dims its glow, the other lantern's appearance seems to shift in a complementary way, even though no light travels between them. Lanterns made long ago in the same workshop, shaped by the same craftsman, may hold a resonance that reveals itself not through sound or sight, but through harmony. When one lantern's glow is revealed, we discover that the other lantern's glow had been part of the same harmony all along. In physics, there is also the idea of a wave pattern describing a particle's possibilities, often written with the Greek letter psi. Instead of imagining this symbol, imagine a soft ripple of moonlight across a pond. The ripple is not committed to a single shape until someone touches the water. Before that, its possibilities shimmer quietly. When two particles are entangled, their ripples merge. They don't have separate ponds. They share the same water, the same moonlight, the same gentle motion. This picture leads to an even deeper thought. What if space itself, the very idea of distance, is not the fundamental thing we imagine? What if the true connections lie in the invisible weave beneath space, the quantum fabric where entanglement lives? In that deeper layer, 2 points can be close even when they're far apart in ordinary space, like two distant stars that share a memory of being born from the same cloud of light, or like two seeds carried by the wind that still echo the same pattern of the tree they came from. Of course, in daily life, this invisible weave doesn't announce itself. When you place a cup on your table, nothing whispers that its atoms are dancing in quantum patterns. Most of the entangled threads around us fade quickly because they brush against the environment. The warmth of the air, the vibration of the floor, the gentle motion of your breath. All these interactions wash away the delicate quantum ripples. Scientists call this process decoherence, but you don't need the term to understand the feeling. It's like writing in the sand near the edge of the ocean. No matter how beautiful the pattern is, the waves eventually smooth it away. Still, just because these threads go unseen doesn't mean they are unimportant. In fact, some physicists believe that entanglement isn't just a mysterious effect, it might be the very glue that holds space together. Imagine the universe as a woven tapestry. If you pulled at the entanglement threads, separating them completely, the tapestry might begin to fray. The smoothness of space, the continuity from one point to another might come apart. This is speculative, of course, but it carries a peaceful beauty. The idea that the universe is held together by relationships, not just by forces. Picture yourself floating above this cosmic fabric, looking down at patches that glow faintly where entangled particles reside. It doesn't feel mechanical or cold, it feels gentle, like a map of hidden connections, always present but only visible when we shine the right kind of light. Each glow corresponds to a quiet agreement written into nature. Even when the particles drift apart, the glow remains, stretching across the dark like a soft bridge. As you imagine this scene, notice how calm it feels. Entanglement often gets described as strange or paradoxical, but seen through this softer lens, it becomes something surprisingly comforting. It tells us that the universe is not a collection of lonely things. Instead, it's a place where relationships exist at the deepest levels of reality, where even the smallest pieces of matter can share a harmony across space. Let this thought settle as gently as a feather falling onto a sheet. The universe, for all its scale and silence, may be filled with a quiet weaving of connections. When we begin to see these threads, not as puzzles to solve, but as patterns to appreciate, the cosmos starts to feel a little less distant and a little more like a vast, beautiful fabric whose design we're only beginning to understand. If you close your eyes for a moment and imagine the universe not as empty space, but as something textured, something with depth and softness, the idea of entanglement becomes easier to hold. Instead of picturing particles as tiny dots floating in a void, imagine them resting on a vast, delicate fabric. This fabric stretches in every direction, farther than your mind can wander, and each point on it is connected to countless others through threads too fine to see. These threads don't tug or snap like ordinary strings. They shimmer gently with the possibilities that quantum physics talks about, and some threads, the entangled ones, shimmer in unison no matter how far apart their endpoints drift. This image is easier to grasp than the formal symbols scientists use. In textbooks, the relationship between entangled particles might be written as a mathematical expression inside vertical bars, or as a combination of two possible states glued together. But instead of imagining those symbols, imagine something softer, two ripples appearing on the same pond. When one ripple changes, the pattern of the other changes too, not because water flows between them, but because both ripples belong to the same surface. They are part of one body, one quiet shape. Entanglement is like that. It is not a message sent from one particle to another. It is a shared texture of the universe's fabric, a single pattern expressed in two distant places. When we measure one particle and force it to reveal one of its possible natures, we disturb the fabric in a way that makes the other particle fall into place within the same pattern. The universe isn't sending a note across space. It's simply showing you that both particles were written into one story. To make this even gentler, picture a wide, handmade quilt. Across its surface are intricate knots, small places where threads cross and tie together. Each knot connects patches that might be far apart on the surface. If you gently pull on one patch of the quilt, a patch on the opposite side might shift, not because anything travelled between them at that moment, but because the threads connecting them were sewn long ago. Entanglement is a connection like that, sewn before the particles separate, quiet, but deeply significant. Another comforting picture is to think of entanglement as a pair of lanterns placed on opposite hillsides. If someone shields one lantern and dims its glow, the other lantern's appearance seems to shift in a complementary way, even though no light travels between them. Lanterns made long ago in the same workshop, shaped by the same craftsman, may hold a resonance that reveals itself not through sound or sight, but through harmony. When one lantern's glow is revealed, we discover that the other lantern's glow had been part of the same harmony all along. In physics, there is also the idea of a wave pattern, describing a particle's possibilities, often written with the Greek letter psi. Instead of imagining this symbol, imagine a soft ripple of moonlight across a pond. The ripple is not committed to a single shape until someone touches the water. Before that, its possibilities shimmer quietly. When two particles are entangled, their ripples merge. They don't have separate ponds. They share the same water, the same moonlight, the same gentle motion. This picture leads to an even deeper thought. What if space itself, the very idea of distance, is not the fundamental thing we imagine? What if the true connections lie in the invisible weave beneath space, the quantum fabric where entanglement lives? In that deeper layer, 2 points can be close even when they're far apart in ordinary space, like two distant stars that share a memory of being born from the same cloud of light, or like two seeds carried by the wind that still echo the same pattern of the tree they came from. Of course, in daily life, this invisible weave doesn't announce itself. When you place a cup on your table, nothing whispers that its atoms are dancing in quantum patterns. Most of the entangled threads around us fade quickly because they brush against the environment, the warmth of the air, the vibration of the floor, the gentle motion of your breath. All these interactions wash away the delicate quantum ripples. Scientists call this process decoherence, but you don't need the term to understand the feeling. It's like writing in the sand near the edge of the ocean. No matter how beautiful the pattern is, the waves eventually smooth it away. Still, just because these threads go unseen doesn't mean they are unimportant. In fact, some physicists believe that entanglement isn't just a mysterious effect. It might be the very glue that holds space together. Imagine the universe as a woven tapestry. If you pulled at the entanglement threads, separating them completely, the tapestry might begin to fray. The smoothness of space, the continuity from one point to another might come apart. This is speculative, of course, but it carries a peaceful beauty. The idea that the universe is held together by relationships, not just by forces. Picture yourself floating above this cosmic fabric, looking down at patches that glow faintly where entangled particles reside. It doesn't feel mechanical or cold. It feels gentle, like a map of hidden connections, always present but only visible when we shine the right kind of light. Each glow corresponds to a quiet agreement written into nature. Even when the particles drift apart, the glow remains, stretching across the dark like a soft bridge. As you imagine this scene, notice how calm it feels. Entanglement often gets described as strange or paradoxical, but seen through this softer lens, it becomes something surprisingly comforting. It tells us that the universe is not a collection of lonely things. Instead, it's a place where relationships exist at the deepest levels of reality, where even the smallest pieces of matter can share a harmony across space. Let this thought settle as gently as a feather falling onto a sheet. The universe, for all its scale and silence, may be filled with a quiet weaving of connections. When we begin to see these threads, not as puzzles to solve, but as patterns to appreciate, the cosmos starts to feel a little less distant and a little more like a vast, beautiful fabric whose design we are only beginning to understand. Imagine standing at the edge of a quiet forest at dusk. The sky is dim enough that shadows start to look uncertain, but bright enough that you can still see the outlines of trees. This is what the boundary between classical and quantum physics feels like. A soft, twilight landscape where things are almost familiar, but not quite. Into this gentle uncertainty stepped a man named John Bell, a physicist with a thoughtful presence and a quiet determination to understand whether the universe truly behaved the way Einstein hoped it did. Bell was not trying to overthrow Einstein. In fact, he began with sympathy for Einstein's discomfort. He liked the idea of hidden instructions, the comforting notion that Particles carried secret information that determined how they would behave when we measured them. It felt orderly. It felt reasonable. It preserved the principle that nothing, absolutely nothing, could influence something else faster than light. But Bell also believed something important. If nature truly obeyed such local hidden rules, then there must be a way to check, to see whether the universe's underlying script was classical and tidy, or whether it held deeper, stranger connections that defied the expectations of Einstein's world. And so, carefully and quietly, Bell devised a way to let the universe answer the question for itself. Bell's idea eventually became known as Bell's theorem, though you don't need to know any of the mathematical expressions usually associated with it. Those expressions include symbols like angled brackets, probability terms, and inequalities. Instead of imagining any of those, picture something simpler, a set of rules for a gentle game played by pairs of particles. The rules say this: if each particle carries its own secret instructions, and if no influence travels faster than light, then there is a limit to how strongly the two particles can agree in the outcomes of their measurements. A limit not set by opinion or theory, but by pure logic. To understand the spirit of Bell's game, imagine two friends who separate and walk into two different parts of a forest. Before they part, they promise to respond to any question with either a nod or a shake of the head, but they cannot communicate once they separate. If you meet each friend later and ask them different questions under different conditions, you can record their answers. If their agreement exceeds a certain level, too perfect, too coordinated, too synchronized, then you know they must have been communicating somehow, or planning in a way that ordinary rules don't allow. Bell realized something astonishing. Quantum mechanics predicted that entangled particles would show exactly this kind of uncanny agreement, a level of coordination impossible to achieve with local hidden instructions. In classical physics, you can only prepare so much in advance. But in the quantum world, the pattern of agreement seemed to dance in a way that defied the limits of any hidden plan. To turn this into an experiment, physicists use pairs of photons, tiny particles of light. They send them in opposite directions, each toward a device that measures something about their orientation, called polarization. Instead of imagining polarization as an angle or a symbol, picture each photon as a tiny arrow pointing in a direction we cannot see. The machines simply ask, is your arrow pointing mostly this way or mostly that way? And for every pair of photons, the researchers compare the answers. Now imagine this happening again and again, thousands of times. The two photons never meet again. They never talk. There is no wire, no radio, no shared memory. They simply start together and fly apart. And yet, when the results are collected, the pattern of agreements between their answers is stronger than what any hidden instructions could possibly produce. Bell had discovered something profound. If hidden local instructions existed, the universe would not behave this way. But experiments showed again and again that the universe did behave this way. The pattern of responses violated the limit, an inequality, that any local hidden system must obey. And so the hidden instruction idea, the comforting picture Einstein hoped for, began to unravel. Still, it's important to clarify what this does not mean. It does not mean that information travels faster than light. It does not mean you can send messages across space by manipulating one entangled particle to affect the other. Many people imagine entanglement as a kind of cosmic telephone line, but it cannot be used that way. The reason is subtle but gentle to understand. The outcome of each measurement is still random. Only when the results from both sides are compared do the correlations appear. And that comparison requires ordinary communication, which still travels at human speeds. So if entanglement does not send messages, what does it do? It reveals something about how the universe writes its stories. It tells us that the world is not built from separate pieces that behave independently. Instead, it suggests that the deepest layer of reality is woven in a way that does not respect the tidy boundaries of classical space. Entangled particles do not influence each other through space. They simply share a single joint identity that cannot be split into independent parts. To make this image softer, imagine a pair of dancers performing a routine. If you watch one dancer alone, you might think they're improvising. But if you watch both dancers together from a distance, you realise their movements are perfectly synchronised, as if they share one choreography. This choreography was not written by communication across the stage, it was shared from the beginning. Bell's work transformed entanglement from a philosophical argument into an experimental question. And when he handed this question to nature, nature answered clearly. The universe does not behave as though each particle carries its own private instructions. Instead, the patterns of entanglement exceed anything classical planning can explain. This realization did not overturn Einstein's legacy. Far from it. Instead, it deepened the mystery he had pointed to. If entanglement is not a hidden signal and not a hidden script, then what is it? What is the quiet thread that binds two particles together, even when vast distances stretch between them? As the night deepens and the next stage of our journey approaches, imagine particles drifting away from each other, not alone, but still softly connected by a pattern older than their separation. The universe has no need to send whispers between them. Their relationship simply exists, and in this quiet fact lies one of the most beautiful secrets ever discovered. A secret Bell helped us see with clarity gentle enough to feel like moonlight touching the ground. If you look around your room right now, everything feels reassuringly ordinary. Your pillow rests where you left it. Your cup stays warm for a little while before gently cooling. The floor doesn't shimmer with possibilities, and your bedside lamp does not suddenly appear in two places at once. Nothing behaves like the spinning coins or glowing beads we described earlier. And if quantum entanglement is truly woven into the universe, a natural question rises quietly in the mind. Why don't we see it? Why doesn't everyday life feel even a little bit quantum? To answer this, imagine dropping a single drop of ink into a perfectly still bowl of water. In the first moment, the ink forms beautiful, delicate curls, intricate patterns that feel almost alive. But very quickly, as the water moves and stirs and shakes, those fragile shapes dissolve. The swirl becomes a blur, the blur becomes a soft cloud, and the cloud becomes ordinary, murky water. This fading of structure is a gentle way to picture what physicists call decoherence, a long word with a simple meaning. Quantum effects like entanglement are extraordinarily delicate. They require stillness, isolation, and silence at a level almost impossible to achieve in the noisy world we live in. The moment a quantum system touches its surroundings, a vibration in the air, a warm photon of light, a stray atom bouncing by, the fine patterns that define its entangled state begin to blur, not because anything breaks violently, but because the environment draws tiny traces of the system's possibilities into itself. If we translated the symbols scientists use to describe this process, they would look like wave patterns being multiplied by endless tiny disturbances. But instead of imagining symbols, imagine a chalk drawing left on a sidewalk. The drawing is crisp and beautiful right after someone finishes it. But then a bird hops by, wind lifts a little dust, someone's footsteps brush the surface, and gradually the sharp lines soften. Nothing dramatic happens, but the drawing loses its quantum-like precision. That softening is decoherence. Now imagine trying to keep a quantum system isolated enough to remain entangled. You would need darkness so complete that no stray photon bumps into it. You would need temperatures so cold that motion almost stops. You would need to shield it from air, from sound, from vibrations, from heat, from dust, from anything that could nudge it. This is why scientists build giant metal chambers, cool their experiments to temperatures near the coldest limits imaginable, and use tools that suspend atoms with magnetic fields. They're trying to keep the chalk drawing from smudging. Quantum effects do not require large, objects. They are most visible when the systems involved are tiny, far smaller than a grain of dust. But this doesn't mean quantum mechanics disappears in the macroscopic world. It simply hides. Everything around you, including you, is made from quantum pieces. But the warmth of your body, the motion of air around your desk, the soft vibrations of sound in the room, all of these create a constant hum of interactions that erase the fragile quantum patterns the moment they form. To make this gentler, think of entanglement as a whisper shared between two people standing in a quiet room. As long as the room stays silent, the whisper is clear and meaningful. But place those two people in the middle of a busy morning market, surrounded by chatter and footsteps and clinking dishes, and the whisper dissolves instantly. Not because the whisper isn't real, but because the environment overwhelms it. Your morning coffee is like that bustling market. The cup contains trillions upon trillions of atoms, all jostling, vibrating, bumping into each other every fraction of a second. Any delicate quantum connection formed between two atoms in that coffee is drowned out almost instantly by the commotion around them. The quantum whisper is lost in a crowd. This may sound like a limitation, but it's actually a blessing. Decoherence is the reason your coffee behaves like coffee, your chair behaves like a chair, and your body behaves like a solid object instead of a ghostly cloud of possible states. It is the process through which the quantum world hands off its delicate uncertainty to the classical world we know so well. It is what allows your day to unfold in a stable, predictable way. Still, the fact that entanglement hides does not mean it is absent. Imagine that underneath your room's familiar surfaces, there is a second kind of world, not separate but underlying the one you see. A world where particles shimmer with potential, where connections stretch invisibly between distant points, where the foundations are soft rather than solid. You live on top of this world every day without ever feeling its presence. Decoherence is the reason. It keeps the deeper layer quiet, smoothing out the quantum ripples so that the familiar world can sit comfortably above them. And yet scientists have learned to peek through the stillness. In laboratories, they create islands of deep quiet, pockets where quantum effects survive long enough to be seen. They trap atoms in perfectly controlled spaces, shield them from noise, cool them until motion slows to a near stop, and in those rare moments of quiet, the quantum world reappears, shimmering softly like moonlight reflected in a perfectly calm pond. In one experiment, researchers managed to entangle two diamonds, tiny but visible to the naked eye, by sending precise vibrations through them. This wasn't science fiction. It was a reminder that entanglement can reach upward into the world we recognize, if only we create the right kind of silence for it to breathe. The lesson is gentle and profound. Entanglement is everywhere, but it is fragile. The world we know is built on top of its delicate patterns, smoothed by warmth and motion and noise. And though we cannot see it in the steam rising from our morning coffee, it is there, woven into the fabric of everything, waiting patiently for the rare places where quiet is deep enough for it to shine. If you step outside on a quiet night and look up at the stars, it's easy to imagine the universe as one enormous singular thing, a grand stage where galaxies spin, planets drift, and life unfolds in its tiny corners. For most of human history, this was the natural assumption. Everything that exists is part of this universe, the only one we can see, the only one we can touch. But as scientists learned more about the early cosmos, an unexpected idea began to creep in slowly and softly. What if the universe isn't alone? What if it's one bubble in a far larger sea? The word multiverse often sounds dramatic, but tonight we'll explore it gently. Not as a chaotic swarm of infinite realities, but as a collection of thoughtful ideas, each one a way to understand why the universe looks the way it does, and why the laws of nature seem so strangely suited for stars, planets, and life. Think of this part of our journey as a quiet stroll through a garden of possibilities, where each pathway leads to a different kind of universe. The first idea is called the inflationary multiverse, but instead of imagining technical diagrams, imagine a pot of water just beginning to boil. Tiny bubbles appear, each forming a little world of its own. In some theories of cosmology, the early universe expanded so rapidly, in a process called inflation, that pockets of space stopped inflating at different times. Each pocket became a bubble universe, sealed off from the others by the stretching fabric of space. Inside one bubble, the laws of physics might look familiar. Inside another, they might be surprisingly different. Not because someone designed them that way, but because the conditions under which each bubble formed were unique. Now imagine drifting from one bubble to another. In one, stars might burn blue, white, and brilliant. In another, atoms might behave in unfamiliar ways. These differences don't come from equations carved in stone, but from the conditions of the early cosmos. It's like kneading dough and finding that some pieces rise quickly, some slowly, and some not at all. Not because the dough is wrong, but because tiny variations in warmth and pressure shape its future. A second idea arises from string theory, which tries to describe particles not as points, but as tiny vibrating strings. Instead of picturing strings with loops and curls, imagine musical notes. Just as different notes arise from the vibrations of guitar strings, different types of particles might arise from the vibrations of these cosmic strings. In this view, the universe resembles a grand instrument. But here's the surprising thought. The instrument might have far more possible songs than the universe currently plays. Different versions of the universe could correspond to different ways the strings settle into harmony. Physicists sometimes call this vast range of possibilities the landscape, not in a literal sense, but as a metaphor for the many forms a universe might take. If you picture a wide field dotted with hills and valleys, each valley might represent a different version of physical laws, a different kind of cosmos. Our universe sits in one valley, but countless others might lie beyond our reach. No equations are needed to imagine this landscape. You only need to picture a quiet meadow, stretching farther than your eyes can see, each dip in the ground a place where a different universe could rest. The third idea, and the one most people associate with the word multiverse, comes from quantum mechanics itself. It's known as the many worlds interpretation, but the name can sound more dramatic than it really is. The idea arises naturally if you take quantum rules seriously and avoid forcing the universe to pick a single outcome when a measurement happens. Imagine a book with many margins, each one containing a variation of a story. When a moment of uncertainty appears, like the spin of a quantum particle, instead of choosing one outcome, the universe allows both. One version of reality sees the particle spin upward, another sees it spin downward. These are not parallel universes created from nothing, but quiet branches of a single unfolding story. You don't feel the branching, because each version of you continues down only one path, unaware of the other. To keep this image soft, think of a garden where many paths diverge. If you take one path, the others still exist. They simply aren't the one you walk. You may hear faint echoes of what could have been, but the world you experience is the one under your feet. Many worlds suggest that quantum events are like countless small forks in the road, each creating a new branch of possibility. It's important to pause here and remember something gentle and grounding. None of these ideas are proven. The multiverse is not a confirmed fact. It is a set of thoughtful possibilities, each trying to explain the mysteries of the cosmos, why space expanded the way it did, why particles behave the way they do, why the universe's laws seem so delicately balanced. These questions themselves can feel almost meditative. You can imagine the universe as a small island of light, surrounded by a vast, still ocean of possible worlds that we cannot see. And in this calm picture, a strange but beautiful idea begins to emerge. Maybe the universe we live in is not the whole story. Maybe it is one petal on a much larger flower, one note in a cosmic chord, one pattern in a tapestry far larger than anything we have imagined. You don't need equations to feel the shape of this possibility. You only need to sit with the feeling that the cosmos might be more generous and more varied than it appears. As we drift deeper into this thought, let your mind imagine a nighttime landscape filled with lanterns. Some lanterns glow softly, others brightly. Some flicker with unfamiliar colours. Each lantern is a universe with its own story, its own rules, its own quiet beauty. Ours is simply the lantern whose light happens to warm us. And as the path continues, you might begin to wonder, if multiple universes exist, could the strange weaving of entanglement tell us something about their connections? Could the threads we've seen linking particles also hint at threads linking worlds? These are questions we will explore gently as the night unfolds and the fabric of possibility stretches softly around us. When you think about your life, it often feels like a single line stretching behind you. A line made of choices, coincidences, and quiet moments, all blending into the path you followed to arrive here tonight. You might remember turning left instead of right one day, or taking a job that led you somewhere unexpected. You may have wondered, in a soft and private way, what would have happened if you had chosen differently. These thoughts usually stay in the realm of imagination. But in quantum mechanics, the idea of what could have happened takes on an entirely new shape, one so unexpected that it gently rewrites how we see possibility itself. This idea is known as the many worlds interpretation, but that name sometimes makes it sound louder and more dramatic than it is. Tonight we'll explore it quietly, with an emphasis on images that help the mind rest rather than strain. No symbols, no equations. Instead, imagine something simple, a path through a wide and peaceful forest. As you walk, you occasionally reach a fork in the trail. One path bends left, the other right. In ordinary life, you choose one and leave the other behind. But in the many worlds view, both paths continue. One version of you strolls down the left route, feeling the leaves crunch beneath your shoes. Another version of you wanders right, hearing a gentle breeze stirring branches in a different direction. Each path holds its own continuity, its own unfolding of moments, its own quiet version of the world. To physicists, the idea emerges naturally when they take the rules of quantum theory seriously. Those rules say that before a measurement is made, a particle does not choose a single option. Instead, it exists in a blend of possibilities, a shimmering overlap of outcomes. In textbooks, this shimmering state is often written using symbols that show multiple possibilities joined together inside vertical bars. Instead of imagining those symbols, picture a spinning coin again, not yet committed to heads or tails. Now imagine two spinning coins entangled with each other. Before they land, they hold a shared cloud of possibilities, outcomes that are not fixed but gently intertwined. When someone finally observes them, classical logic demands a single result. But quantum logic, taken at face value, suggests that reality doesn't collapse to just one outcome. Instead, it unfolds into multiple branches. In one branch, the coins land heads and tails. In another branch, tails and heads. Each outcome becomes its own continuation. The many worlds idea simply says, rather than forcing one outcome to be real and the others to vanish, the universe carries them all forward, like parallel chapters in a single book. The chapters don't mix. They don't influence each other. They drift apart softly, separated by the ever-growing effects of decoherence. The quiet process we talked about earlier that washes away quantum patterns when systems meet the noisy environment. Decoherence acts like a curtain that falls between branches, making each one private and isolated. To make this clearer, imagine writing with ink that spreads into several lines at once. As the lines extend, they diverge and become their own stories. Over time, the ink dries and the stories no longer touch. Each one is complete, whole, and unaware of the others. You, in your everyday life, experience only one of those stories, one of those threads of ink. But the many worlds perspective imagines that all the other threads continue too, quietly, independently, like parallel rivers flowing through a vast landscape. It can feel strange at first. We're used to the idea that reality is singular, but quantum mechanics challenges that intuition, whispering that the universe might be more like a branching tree. The trunk begins at the same point, the moment of creation, but at the tiniest scales, branches emerge constantly. Every quantum event, every superposition that resolves into a definite outcome, gently adds another twig to the cosmic tree. This doesn't mean that every thought you have splits the universe. It doesn't mean your decisions create dramatic new worlds. Instead, the branching mostly happens at the microscopic level. Particles choosing among possible spins, photons taking one path or another through an experiment, atoms vibrating in slightly different patterns. These tiny branches over time accumulate and spread, gradually widening into distinct versions of reality. To keep this idea gentle and sleep-friendly, imagine a great library filled with countless books. Each book begins with the same opening pages: the birth of the universe, the formation of stars, the shaping of planets. But after a certain point, the books subtly diverge. One version of Earth has a thunderstorm on a summer day, another has clear skies. One version of you chooses tea tonight, another chooses water. These differences are tiny, almost invisible. Yet over billions of years they create universes that drift quietly apart like ships sailing into different horizons. It's important to remember that many worlds is just one interpretation of quantum mechanics. It doesn't introduce new rules, it simply interprets the existing rules in a particular way, a literal way. Instead of assuming that the universe must pick one outcome, it accepts that quantum possibilities continue to coexist. Other interpretations see things differently, and none has been proven to be the absolute truth. That's part of the beauty. Physics leaves room for wonder. Another key point is that these branches cannot communicate with each other. The decoherence curtain is too thick. In the mathematical language, the states that describe different branches no longer overlap. But instead of imagining symbols, picture melodies drifting apart. Two songs that begin in harmony, but slowly separate until you can no longer hear one from within the other. Reality, in this view, is a collection of melodies played by the universe, each one carrying its own version of events. Some people find the many worlds idea unsettling, others find it strangely comforting. The idea that possibility isn't lost, that every path exists somewhere, even if you only walk one of them. In a calm moment, you might imagine that somewhere in the quiet branching of reality, another version of you took that other path, learned something new, or made a choice you didn't. But that version isn't a ghost or a rival. It's simply part of the vast landscape of possibility. As you let this image settle, imagine once more the forest, with many trails. You walk only one path tonight, hearing the crickets and feeling the cool air against your skin. The other paths remain, quiet and undisturbed, stretching softly into the darkness. And somewhere, in one of those other branches of the cosmic tree, another version of the story continues, gentle, separate, and entirely unaware of this one. As we move gently through this nighttime exploration, it's easy to feel the many worlds idea settling into place like a soft blanket. It has a certain poetry to it, countless branches, countless versions of reality, all drifting quietly apart. But the story of quantum physics is richer than any single interpretation. Physicists, in their patient attempts to describe the unseen world, have proposed several different ways of understanding what lies beneath the shimmering layer of possibilities. None of these interpretations require equations tonight. None require strange symbols or dense diagrams. Instead, we'll explore them through calm imagery, letting each idea take shape naturally, like lanterns coming into view along a dim forest path. Let's begin with one of the gentlest alternatives, pilot wave theory, sometimes called the Bohmian interpretation. If many worlds suggests a garden full of branching paths, pilot wave theory offers something simpler, something more classical in feeling. It says that every particle has a definite position at all times, a definite trajectory, like a tiny boat floating on a vast and subtle ocean. But this ocean isn't ordinary water. It is a hidden wave, smooth, continuous and guiding, that determines how each particle moves. Instead of imagining mathematical wave symbols that look like curled lines, picture a quiet tide rolling beneath a small wooden boat. The boat never gets lost. It simply follows the current shaped by the wave underneath. In this view, quantum weirdness comes not from particles being in two places at once, but from this guiding wave being more complex than anything we can see. The wave doesn't obey local rules. It can stretch across space in ways that make entangled particles appear instantly correlated, not because they communicate, but because the wave guiding them is one shared entity. Like two boats riding the same long, gentle swell of the ocean, their motions remain coordinated even when they drift far apart. The hidden wave does the work. Pilot wave theory doesn't need multiple universes. It simply gives the particles a quiet ocean to travel on. Now, let's take another lantern from the path: relational quantum mechanics. This idea steps away from the notion of absolute facts and replaces them with something softer. It suggests that the properties of a particle, like its position, its energy, its spin, are not fixed things that exist independently. They exist only in relation to something else. To make this less abstract, imagine two friends who can only describe themselves when they are together. One might say, "I'm taller than you," or "I'm smiling because I see you smiling." Their identities take form through their relationship. In relational quantum mechanics, a particle doesn't carry a single global truth. Instead, it carries truths that depend on how it interacts with another system. A measurement doesn't uncover a hidden property. It creates a relationship. In this soft picture, reality is not a rigid tower of facts, but a web of interactions, like dew-covered threads in a spider's web that only shine when the morning light touches them. Each glimmer represents a property revealing itself through a connection. Continuing down the path, there is another interpretation that feels more philosophical, almost introspective. Cubism, short for quantum Bayesianism. You don't need to know what Bayesian probability is. We won't use any formulas or symbols tonight. Just imagine walking through a foggy landscape where visibility is limited. You carry a small lantern, and the glow illuminates only a few steps ahead. The choices you make are informed by what you expect to find in the fog, even though you cannot see it clearly. Cubism sees quantum mechanics not as a map of objective reality, but as a tool for guiding an observer's expectations. The wave pattern descriptions used in quantum theory, often written with curving psi-like symbols, aren't treated as physical things, but as expressions of belief. They describe what an observer expects to see based on their experience, not what the universe absolutely contains. In this view, measurement is not a sudden collapse of the world, but simply the moment your lantern light reveals what was hidden in the fog. These interpretations, many worlds, pilot wave, relational quantum mechanics, cubism, are not enemies. They're gentle companions trying to explain the same strange dances of the microscopic world. They all agree on the experiments, they all agree on the predictions. They differ only in the stories they tell about what is happening beneath the surface. It is as though nature is a beautifully written poem, and different readers offer different interpretations, each one illuminating a different nuance of meaning. Even within mainstream physics, the question, what is really happening, is treated with quiet humility. Some physicists see the interpretations as optional, like choosing a comfortable pair of shoes for a long walk. Others see them as essential clues, pointing toward a deeper truth we haven't yet uncovered. But what matters most is that none of these interpretations claim to be final. They are attempts to whisper meaning into the quantum world, not to shout certainty. If we follow these whispers, a pattern begins to emerge. Each interpretation offers a different perspective on entanglement. In many worlds, entanglement is the branching structure of reality itself. In pilot wave theory, entangled particles are boats connected by the same hidden wave. In relational quantum mechanics, entanglement is a relationship waiting to be revealed between systems. In cubism, entanglement shapes the expectations an observer brings to their encounter with nature. Despite their differences, all these stories circle around the same mysterious truth. The universe is more connected, more relational, and more subtle than classical physics ever imagined. The quantum world does not behave like a collection of isolated parts. It behaves more like a tapestry, with each thread influencing the weave. As the night deepens, let these different interpretations drift gently in your mind like soft lanterns on a still lake. Their reflections shimmer, overlap, and separate again, each offering a slightly different view of the same deep water. You don't need to choose one. You can simply appreciate the quiet beauty of the possibilities, the many ways of understanding a world that refuses to be pinned down by a single story. And quietly, in the background of all these interpretations, the question at the heart of our journey waits. If the universe is so deeply interconnected, could these connections extend beyond a single world? Could quantum entanglement be more than a pattern within one reality? Could it hint, however softly, at threads that run between worlds? There's a quiet moment in every scientific journey when the facts and equations settle gently into the background, and what remains is a question, a soft, lingering thought that hovers like a lantern over calm water. Tonight, as we enter this new stretch of our exploration, we find ourselves at that moment. We've seen how entanglement binds particles across space, how it resists classical explanations, and how different interpretations of quantum mechanics offer different stories about what these invisible ties might mean. And now, with the night deepening around us, we can finally ask the question that has been waiting patiently beneath all the others. Could quantum entanglement be, in some sense, a thread that links not just particles, but entire branches of reality, perhaps even different universes? Before we wander too far, we need to walk carefully. In mainstream physics, the reliable, experimentally grounded part, entanglement lives entirely inside one universe. It is a feature of a single quantum state, described not by machines or magic, but by relationships between particles. In that picture, entanglement is a pattern inside a single fabric. Nothing crosses between universes because, as far as experiments show, we only have one universe to measure. But there is another way to look at this, not as a replacement for the science, but as a gentle extension of imagination guided by physics. If entanglement already shows us that two distant points in space can share a single story, could that idea be stretched, softly and carefully, to wonder whether two different realities might share a deeper connection? Not as a proven fact, and not as a mechanism, but as a possibility worth contemplating. To ease into this, imagine reaching into your pocket and pulling out a pair of headphones that have somehow tied themselves into impossible knots. The wires twist around each other in ways you don't recall creating. Some knots belong to one strand, some wrap around both, and some seem to lock the two parts together so tightly that you can't untangle one without disturbing the other. Entanglement is a little like that. If different branches of reality exist, different outcomes, different timelines, perhaps their wires were tangled at the moment of creation. Perhaps the universe didn't come into being as a clean, separate stack of worlds, but as intertwined strands of possibility. Another soft analogy is to imagine an old-fashioned radio. When you tune it to a station, the sound that fills the room comes from invisible waves passing through space. But those waves don't exist only for your radio. Countless radios can tune to the same signal. Each device produces its own sound, its own texture, its own small world of music or quiet chatter, yet all of them are expressions of a single shared broadcast. If universes are like radios, then entanglement might be something like the signal, an underlying pattern that different realities can resonate with, each in its own way. Of course, this is imagery, not physics. Real-world entanglement does not allow radios to talk across dimensions. It doesn't permit signals to jump between worlds, nor does it let one branch of reality nudge another. But the image helps us feel the idea of a deeper coherence, a shared foundation beneath apparent separations. There's also something compelling about how entanglement behaves when systems branch in the many-world sense. In that interpretation, when a quantum measurement happens, the universe doesn't choose a single outcome. Instead, the universe gently branches, like a quiet river dividing into two streams. In one branch, a particle spins upward, in another it spins downward. Yet the particles remain perfectly correlated in each branch. Their entanglement doesn't vanish, it simply splits, maintaining a consistent story across all versions of reality. It's as if entanglement is not just a connection between particles, but a rulebook that defines how branches unfold. If this is true, even in a poetic sense, then entanglement becomes more than a pattern in our universe alone. It becomes the structure along which reality spreads. Like the beams beneath a wooden bridge, or the roots beneath a forest floor, entanglement could be the hidden support holding multiple branches of existence in alignment. We should pause to be honest. No experiment has ever shown entanglement reaching into other universes. Physics, as practiced in laboratories, remains grounded in what we can measure here. But physics also leaves room for inquiry, especially at the edges where our understanding begins to blur into mystery. As long as we walk softly and clearly separate fact from imagination, we can explore without becoming lost. And so we imagine entanglement not as a telephone line or a gateway, but as a kind of cosmic thread, a connective tissue woven quietly through the fabric of possibility. If there are multiple branches or multiple universes, then entanglement could be one of the foundational patterns they inherit. It could be the soft echo of their shared origin, the gentle reminder that different realities might arise from the same deeper wave of creation. To hold this idea in your mind, picture again the tangle of headphone wires. Imagine that each strand is a universe, a path of events, a story of stars and planets and people. Some strands never touch, some cross briefly and diverge, and some are knotted tightly, sharing a twist or loop that neither can undo without the other. These knots, in our metaphor, are entanglement, not bridges you can walk across, not portals or doors, but shared twists in the deeper material of existence. Or think again of the radio signal. Each radio plays its own music, its own voice, its own world of sound. But underlying them is the same invisible wave. If universes are like radios, perhaps entanglement is one of the frequencies they share, a subtle resonance woven into their foundations. None of this alters the hard boundary of physics as it stands, but imagination, when guided gently, can help us appreciate the profound strangeness of a universe that allows entanglement in the first place. Even if entanglement belongs entirely to one universe, its existence is still astonishing. And if reality extends into branches or parallel worlds, then entanglement might be one of the quiet hints that all these realities are siblings, not isolated strangers, but parts of a single, immense, interconnected tapestry. As the night continues, hold this idea like a small glowing ember, that beneath everything we see, beneath everything we think we know, the universe may be threaded with patterns finer and more mysterious than any story written on its surface. Patterns that link not just places, but possibilities. If you sit quietly for a moment and imagine the universe as a vast, soft fabric stretching in every direction, you may begin to picture space itself as something that can be bent, folded, or stitched in unseen ways. This fabric is not cloth, of course. It is the structure of space-time, the quiet stage on which all events unfold, and tonight we venture into one of the most delicate and imaginative ideas in modern theoretical physics. The suggestion that entanglement and the geometry of space-time might be two faces of the same deeper truth. The idea has a name that sounds almost like a riddle. EPR. But rather than thinking of it as a cryptic equation, imagine it as a gentle whisper proposing that two seemingly different things may be quietly related. The ER part refers to Einstein-Rosen bridges, tiny theoretical connections in the geometry of spacetime that people often call wormholes. The EPR part refers to the Einstein-Podolsky-Rosen paradox, the original puzzle that brought entanglement into the spotlight, and the conjecture simply says this: perhaps these two ideas are reflections of a single phenomenon. To bring this to life without symbols or diagrams, imagine again our fabric of space-time. In some places the fabric may stretch, in others it may ripple, and in extremely rare and subtle places it might fold or twist so delicately that two distant points become close, not in the space we see, but in a deeper geometric sense. These tiny folds, if they exist, would be like microscopic seams, not tunnels we can travel through, not pathways for messages, but quiet bridges that exist only as part of the universe's hidden structure. Now imagine two particles that are entangled. Their behaviours remain coordinated even when they drift far apart. Physicists who study quantum gravity notice that this kind of correlation resembles what might happen if 2 points of spacetime were connected by a miniature non-traversable bridge. A bridge so small and so fragile that no object, no light beam, no signal could ever pass through it. The bridge would not be a tool, it would not be a door, it would simply be existing as part of the underlying pattern. This is the heart of the EPR idea. Entanglement may create the same kind of connection that, in the language of geometry, we describe as a wormhole, and wormholes in turn may simply be what entanglement looks like when translated into the language of space-time. This doesn't mean wormholes pop open between particles. It doesn't mean two electrons are secretly connected by tunnels. Instead, think of the bridge as an image for a relationship. Just as you can draw a line between two close friends on a social network map, but no message travels through that line directly, the bridge in EPR is a symbol for the connection that entanglement creates. The bridge is not a highway, it is a quiet trace of relationship. To make this even softer, imagine two embroidery threads sewn into a piece of cloth. Each thread might lie far apart on the surface, but deep inside the fabric, they may be knotted together by a stitch you cannot see from above. When you pull slightly on one thread, the other reacts, not because there is a tunnel between them, but because the hidden stitch ties their fates. In this gentle metaphor, entanglement is the knot, and space-time is the cloth. Some physicists take this idea further and wonder whether space-time emerges from the totality of these stitches. Imagine space as a quilt, its smoothness and shape determined not by individual pieces, but by the intricate web of threads holding everything together. If you remove enough stitches, the quilt begins to fall apart. In this picture, if you could remove all entanglement, space itself might unravel into something unrecognizable. The fabric would lose its structure, the universe its continuity. It's important to emphasize that EPR is not proven. It is a bold, imaginative hypothesis proposed to help reconcile quantum mechanics with the curvature of space-time described in general relativity. It exists at the frontier of theoretical physics, where ideas are tested for coherence and beauty long before experiments can touch them. Tonight, we treat it gently, as a possibility worth contemplating, not a final answer. Now, let's softly imagine how this could relate to the idea of multiple universes. If entanglement shapes the geometry of space-time in our universe, could similar stitches exist between entirely different universes, if such universes exist at all? Not as wormholes one could travel through, and not as lines of communication. Instead, imagine two separate quilts sewn from the same original thread bundles. Though the quilts are distinct, the threads inside them may carry echoes of a shared origin. Entanglement might be a quiet reminder of that inheritance. Of course, we cannot test this. We do not know what lies beyond our cosmic horizon or whether other universes truly exist. But the imagery helps us feel something subtle. That entanglement may be more than just a strange quantum effect. It may be part of the architecture of reality, a structural feature rather than a fleeting phenomenon, a whisper of geometry hidden inside the relationships between particles. The more scientists study entanglement, the more they suspect it may play a role in shaping the very shape of space. And if that is true, then entanglement is not merely a connection across distance, it is a connection across existence. A pattern that stitches the universe together from the smallest scales to the largest. Let your mind rest for a moment on this image. A vast, silent fabric illuminated only by faint starlight. Across its surface, tiny invisible stitches hold distant points together in ways we cannot see. These stitches are not shortcuts for travel. They are not portals. They are simply part of the design. Quiet, unnoticed, essential. EPR invites us to consider that entanglement is one of the universe's sewing techniques, and whether this stitching applies only within our world or hints at something across many worlds, the idea itself is gentle and strangely beautiful. It reminds us that the universe may be held together not by rigid laws alone, but by relationships. Patterns of connection woven through everything that exists. When you think back through your own memories, you might find that some events stand out more vividly than others. A conversation, a walk, a choice you made. Yet each moment, no matter how small, shaped the story of your life. In quantum mechanics, the story of the universe is similar, woven from countless moments where possibilities narrow into outcomes. But in the many worlds view, those possibilities never truly disappear. Instead, they drift into separate branches, each one carrying its own version of events forward. And if entanglement plays a role in these branching moments, then somewhere deep beneath the surface of reality, it may be quietly carrying the memory of how and where the branches split. To approach this gently, imagine a large tree at the edge of a field. Its trunk is thick and ancient, but its branches stretch in many directions. Some branches split early, growing apart quickly. Others diverge much later, remaining close until the very last moment before separating into different paths. Entanglement, in this imagery, is the shared memory deep within the trunk, the pattern that the branches inherit. The branches grow apart, but the connections that link them trace back to the same shared source. In the many worlds interpretation, quantum measurements don't collapse anything. Instead, the universe continues smoothly, and the different outcomes of a single quantum event simply proceed along different branches. Consider a small quantum particle with a property that can point up or down. Before the measurement, its state is like a soft shimmer of both possibilities. When someone measures it, the world gently branches. In one branch, the particle is found pointing upward. In another, it is found pointing downward. You don't feel this branching. Decoherence ensures that once the branches form, they can no longer interact. But the structure remains. Two outcomes, two paths, two realities. Now imagine that this particle is entangled with another. Entanglement means the particles do not carry separate stories. Instead, they share a single narrative. If you measure one particle and find it pointing upward, then in that branch of reality its partner will always show the complementary result. And if you measure the first particle and find it pointing downward, then in that branch the companion will respond accordingly. Entanglement ensures that the two results stay coordinated across the branching. To keep things soft, imagine two dancers performing a duet. Before the music begins, each dancer doesn't know exactly which movement they will perform, only that whatever movement they do will match what the other dancer does at the same moment. When the music starts, the dancers separate across two stages. On one stage, the dancer lifts their right hand. On the other stage, the dancer lifts their left. These stages are like branches, parallel performances that never touch. And yet, in both performances, the movements remain perfectly coordinated. The choreography, written before the separation, is preserved. That choreography is entanglement. If universes truly branch, then entanglement plays the role of a quiet guide, ensuring consistency in every branch. But that leads to a deeper question, one with a soft philosophical shimmer. Does entanglement simply follow the branching, or does it help define where and how branches split? It's not a question with a definitive answer, but it's a beautiful one to hold. It may help to imagine the quantum world as a great tapestry being woven continuously by unseen hands. The threads represent possibilities. When certain threads twist together, creating entanglement, the weave gains structure. The moment a measurement is made, the moment an outcome becomes defined, the tapestry divides into layers, but the shared twists remain recorded within each layer. In this picture, entanglement isn't just a connection, it's a kind of memory, a record of how different strands once intertwined. Some physicists, thinking carefully about many worlds, point out that entanglement describes which branches are compatible with each other. In one branch, the first particle points upward and the second downward. In another, the first particle points downward and the second upward. But there will never be a branch where both point upward or both downward if the rules of their entanglement forbid it. In that sense, entanglement is like a quiet librarian keeping track of which stories are allowed to be written and which ones can never exist. Now let's turn toward the idea of you in these branches. In everyday life, you feel whole and singular. But in the branching view, there are many versions of you, not duplicates, not ghosts, just different continuations. These versions cannot meet. Decoherence keeps them forever separated, but if entanglement underlies branching, then every version of you inherits a piece of a deeper structure, not in a mystical sense, but in a technical one. If the atoms in your brain were once entangled with something else, each branch carries a consistent echo of that past entanglement. It does not give you knowledge of other branches, as it shapes the version of reality you experience. To picture this gently, imagine a lock with two keys. One key exists in your branch, the other in another branch, but both were cut from the same original mould. Neither key can travel across branches, and neither key knows about the other. But their shapes, their patterns, are linked by a shared origin. They are not copies. They are twins separated by a curtain. When physicists say that you might be entangled with other versions of yourself, they do not mean this in a mystical or spiritual sense. They mean it in the quiet, technical sense that the atoms composing your body might once have shared quantum relationships with other systems, and those relationships could have branched along with everything else. The entanglement is not communication. It is not influence. It is simply part of the structure of the universe's unfolding. And yet there is something strangely comforting in this picture. You are not a lone point drifting in a single timeline. You are part of a vast branching of possibilities, each outcome moving softly forward in its own world. You may never speak to those other versions, and they may never speak to you. But the existence of those branches, and the entanglement patterns that guide them, suggests that reality is not a narrow path, but a broad, shimmering forest of possibilities. As we rest in this thought, imagine again the tree at the field's edge. Its trunk is thick, its branches countless. You stand beneath it, feeling its presence, its age, the quiet strength of its structure. The branch you follow is only one of many, but all branches share the same roots, the same beginning, the same deep memory. And somewhere in that memory lies a web of entanglement, delicate, silent, and profoundly beautiful. As our journey deepens, a natural curiosity begins to rise, soft at first, then persistent, like the faint glow of dawn slowly illuminating the horizon. If entanglement is truly a connection, if it threads particles together across space and even seems to guide the branching of reality itself, then a quiet question emerges almost on its own. Could anything ever pass between these threads? Could information slip even faintly between universes? It is a question whispered in late-night conversations, explored in stories, imagined in dreams. And tonight we'll explore it too, gently, honestly, without drifting into claims that science cannot support. To begin, imagine two neighbouring rooms separated by a heavy curtain. In each room, people speak, laugh, and live their own stories. If you press your ear against the curtain, you may hear vague murmurs, hints of activity, echoes of life. But no clear message passes through. The curtain is too thick, the fabric too dense. The sound is muffled into something more like a vibration than a voice. This curtain is a useful metaphor for what separates one branch of reality from another. Decoherence erects a barrier so complete, so instantaneous, that the worlds diverge faster than anything could slip between them. In mainstream quantum mechanics, this curtain is absolute. Entanglement cannot be used to send messages, not across distances within one universe, and certainly not across different universes if they exist. The reason is subtle, but we can understand it without symbols. When two entangled particles are measured, the outcomes match in coordinated ways, but each measurement by itself looks random. Imagine flipping a coin and always getting a random result, even though someone far away flips their coin at the same moment, and the two coins always complement each other. Neither person can control their coin, neither can force it to land heads or tails, and because of that, neither can send a message. Coordination isn't communication. Even if universes branch in the many-world sense, and even if entanglement helps structure those branches, the rules remain unchanged. What happens in one branch cannot be used to control or reach into another. The branches separate too quickly, too thoroughly, as if carried away by diverging winds. Still, the idea of information bleeding is intriguing, and to explore it gently, we have to consider what scientists mean by information in the first place. In physics, information is not like a letter you mail or a text message you send. It is more like a description of the state of a system, the arrangement of its pieces, its potential behaviours, the way its parts relate. When physicists write equations using symbols or angles or absolute value bars, they're simply capturing that structure. Instead of imagining those symbols, picture them as the labels on a library shelf telling you how the books are arranged, not telling you the stories themselves. In quantum mechanics, the most interesting information is the kind that describes relationships, how two particles are linked, how their possibilities overlap, how their futures depend on one another. This relational information is what entanglement expresses, but relational information isn't something that travels. It isn't a message courier that crosses boundaries. It is the quiet shape of a connection, not a channel for sending thoughts or signals. Some speculative models explore whether the process of collapse, the moment when quantum possibilities resolve into definite outcomes, might behave differently under extreme conditions. But rather than thinking of collapse as a sudden jolt, imagine it as a gentle settling of dust after a breeze. Some proposals wonder whether gravity plays a role in this settling. Others wonder whether superpositions, those shimmering overlaps of possibility, might persist longer than expected in certain situations. These ideas are technical and fragile, like early sketches in a notebook, and so far, none have provided evidence that information could leak from one branch of reality to another. To keep the picture soft, imagine a series of waterfalls flowing from a high mountain. Each waterfall splits into smaller streams as it descends. Once separated, the streams no longer mix. They flow into different valleys, watering different fields, feeding different rivers. The branching is simple and irreversible. The streams may share a common source, but once the water diverges, its path is set. In the same way, quantum branches share a common origin, but once they separate, they drift too far apart for anything to cross between them. Even in physics that entertains the idea of multiple universes, whether bubbles in a cosmic foam or branches in a quantum tree, the picture of information transfer remains the same. Separation is separation. The curtain, the waterfall, the diverging streams, the split paths, they all describe a boundary that is not meant to be crossed. And yet, there is something beautiful in this limitation. The fact that we cannot speak to other branches or send messages across universes reinforces the integrity of the life you are living now. It means your experiences, your memories, your choices, your regrets and triumphs all belong uniquely to you. They are not overwritten or altered by unseen versions of yourself. They are the private melody of your timeline, unshared and undisturbed. But even if the branches cannot exchange information, they still tell us something profound. That reality might not be a single line, but a shimmering tapestry of possibilities. If entanglement is a thread that stretches through this tapestry, then the same pattern that governs particles here might exist in countless other places, not as a portal, but as a signature, a quiet echo of how the universe structures possibility itself. To rest with this idea, imagine standing in a vast hall filled with mirrors. Each mirror reflects you not as a single image, but as countless variations, slightly different angles, different lighting, different expressions. You cannot step into those reflections, and they cannot step into yours. But their existence reminds you that perspective shapes reality, that what is seen in one mirror may differ from another, even though the light creating all the reflections comes from the same source. In that sense, entanglement may not connect worlds, but it may hint at a deeper unity, a shared mathematical origin that branches into many forms, and even if no information can bleed between universes, the possibility that they exist at all adds a soft, shimmering layer to our understanding of the cosmos. It invites us to imagine reality not as a single melody, but as a vast orchestra, each instrument playing its own part, all arising from the same initial burst of creation. As we leave this question behind, let the thought settle gently. The universe protects its branches, keeps them separate, maintains the privacy of each unfolding story. And yet, through the quiet pattern of entanglement, we glimpse the subtle structure that all these stories share. If you listen closely to the scientific world today, beneath the noise of headlines and the hum of everyday discovery, you can hear a softer, steadier rhythm, the rhythm of a frontier quietly expanding. It's something like the early days of flight or the first experiments with electricity. Small steps that feel humble on the surface, yet carry the potential to reshape the distant future. Tonight, we step gently into that frontier, a place where entanglement is no longer just a curiosity of theory, but a tool scientists are learning to harness, protect, and weave into the technological fabric of the world. Imagine, for a moment, a beam of light drifting through the night sky. Light seems simple, something you switch on in your bedroom without thinking. But in modern experiments, light becomes a messenger of quantum information. Each particle of light, each photon, can carry delicate entanglement across great distances, provided we can shield it from the chaos of the environment. For years, maintaining entanglement across a laboratory table was considered a major triumph. Today, scientists have sent entangled photons between mountaintops, across lakes, and even between Earth and orbit. One of the most poetic demonstrations of this was achieved through a satellite orbiting silently above the Earth. Rather than imagining technical diagrams or formulas describing spacetime trajectories, picture a small silver sphere floating through the darkness, releasing faint threads of entangled light downward, like tiny shooting stars descending toward mountaintop stations. Each photon's journey ends in a detector, waiting patiently in the cold night air, ready to record a whisper of entanglement that has travelled hundreds of kilometres. In this way, space itself becomes a carrier of the quantum weave. The fragile connection holds, not perfectly, not always, but enough to show that entangled light can survive the long fall through our atmosphere. From experiments like this grows the dream of a quantum internet. Not an internet of faster downloads or high-definition videos, but an internet of security and subtlety. A network where information is encoded not in large pulses of electricity, but in the delicate quantum states of particles. In such a network, a message cannot be intercepted without disturbing the entanglement that protects it. Imagine two distant cities connected by invisible quantum threads. When one city tries to share a secret key with the other, the entangled connection ensures that any eavesdropper leaves a detectable trace. The system reveals the intrusion, quietly but unmistakably. It's not magic. It's the quantum world protecting its own fragility. To make these systems real, researchers must learn to maintain entanglement in increasingly large objects. Not just individual photons or ions, but clusters of atoms, small mechanical devices, even tiny mirrors cooled to near absolute stillness. To picture this, imagine a miniature tuning fork no bigger than a dust grain. Its prongs vibrate so gently that even a whisper of heat could disturb them. Yet scientists are finding ways to entangle these vibrations, linking them with the delicate dance of photons in a cavity. Two such tuning forks, resting in separate chambers, can behave as if they share a single quiet rhythm. It's a small step toward entangling macroscopic objects, toward bringing quantum harmony into the everyday scale of things. And as systems grow, they teach us more about the limits of entanglement. When will it break? What disturbs it most? How far can it stretch? Each experiment is like testing a new kind of thread. In some conditions, the thread holds strong. In others, it dissolves into the noise of the environment, the same way a breath of wind erases a chalk drawing on a sidewalk. Learning how to protect these threads doesn't just unlock technology, it teaches us something about the nature of the threads themselves. As we follow these developments softly, imagine a world where entanglement becomes part of everyday life. Not in loud or fantastical ways, but in quiet ones. A bank that secures its communication with quantum keys. A spacecraft sending its diagnostic data through entangled channels. Hospitals using quantum sensors to detect subtle shifts in the body. Each application relies on the same principle. Entanglement is a bond so delicate that any attempt to tamper with it leaves unmistakable fingerprints. Yet beneath these practical dreams lies something more philosophical. As we learn to weave entanglement on demand, to shape it, to preserve it, we begin to glimpse its deeper character. We discover that entanglement is not just an abstract rule of quantum theory, it is a resource, a structure, a part of reality that can be sculpted. And so, a larger question returns. What is entanglement really? A tool? A guideline for how the world behaves? A shadow of a deeper geometry? Or something even more profound? A basic ingredient of existence itself? This is where the multiverse question quietly slips back into the conversation. If entanglement underpins the architecture of space-time, as some theories hint, then the patterns we are learning to manipulate in laboratories may also reflect the patterns that shape reality at the larger scales. If we are learning to weave and unweave these threads with increasing finesse, perhaps we are coming closer to understanding how the universe wove them in the first place. Imagine a craftsman sitting before a loom, threading strands of colour through a tapestry. At first you see only the surface pattern, the visible design. But if you watch the craftsman's hands long enough, you begin to understand the deeper structure, how tension is balanced, how threads cross, how the entire fabric holds together. In the same way, experiments with entanglement are our first glimpses into the hands of the universe, the subtle motions that bind everything, from particles to planets, into a coherent whole. We don't yet know what this means. We cannot say whether entanglement is merely a feature of one universe or a fingerprint left by deeper layers of reality. But as we learn to handle these threads, we do more than build technology. We build familiarity, understanding, intuition. And perhaps in this growing understanding lies the seed of an answer. Not a loud declaration, but a quiet intuition that entanglement may be showing us what reality is made of, one delicate thread at a time. There's something quietly humbling about sitting with the idea that the universe might branch, shimmer, or ripple beneath the surface we normally see. We can talk about photons, particles, and entanglement with calm detachment, but eventually the mind drifts back to a softer, more personal question. Where do we fit into all of this? What does it mean for a human being, someone who breathes, thinks, forgets, dreams, to live in a universe built from possibilities? This is where our journey turns inward, not toward mysticism or grand claims, but toward the gentle boundary where physics meets experience. A boundary woven from curiosity, not certainty. To begin, imagine yourself standing at the edge of a forest path at dusk. The light is fading just enough that the world feels a little uncertain. Shadows stretch long, colours soften, and your senses sharpen in subtle ways. The forest has not changed, but your perception of it has. In quantum mechanics, measurement is a bit like that. The act of observing does not necessarily impose a dramatic change on the world, but it shapes what you perceive as real. It clarifies the path your branch of reality will follow. Scientists sometimes write this process using symbols that show how a shimmering combination of possibilities settles into a definite outcome. Instead of imagining these symbols, imagine that dusky forest settling into night as you choose one path to follow. The branching doesn't require magic. It doesn't require intention. It is simply how the universe unfolds when possibility turns into experience. But your choices, which experiments you perform, what you decide to measure, influence which branches you will inhabit. There is nothing supernatural about this. It does not give your mind the power to rewrite physics. It simply means the observer participates in selecting which aspect of the quantum world becomes part of their story. Your decision to look left or right on that forest path determines which direction you walk. It does not move mountains or rearrange the trees. Still, the thought carries a soft emotional weight. In a universe where many outcomes exist somewhere, the particular sequence of moments that led you here, to this night, to this breath, to this quiet listening, becomes something both fragile and precious. The infinite branches remain unreachable, yet your branch is uniquely yours. This brings us to one of the gentlest questions people ask about quantum mechanics. Does consciousness play a special role? Over the years, this idea has drifted across books, movies, late-night conversations, often inflated into something dramatic. But physics gives a much calmer answer. Measurement does not require a human mind. A detector can observe. A beam splitter can observe. A grain of dust can observe. In physics, observation simply means interaction, when two systems meet in a way that records a fact. To make this less abstract, imagine snow falling onto a field. Each snowflake leaves a mark on the ground. That mark is a record, a measurement. It doesn't require awareness. It doesn't need thought. The world interacts with itself constantly, and those interactions create the classical reality we walk through. Consciousness doesn't collapse a wave pattern with intention. It simply experiences the result already shaped by the world. Yet consciousness is still extraordinary in another sense. Not magical, but quietly profound. Your mind is a processor of information, a structure built from billions of neurons humming softly, like a vast network of tiny lanterns glowing in the dark. These neurons are made of particles, and those particles follow the rules of quantum mechanics. Some early proposals, delicate, often speculative, wondered whether entanglement might play a role in how the brain knits together thoughts. But so far there is no convincing evidence. The brain is warm, messy and noisy, a place where delicate quantum patterns fade almost instantly. If entanglement survives in the brain at all, it is fleeting, overwhelmed by the many interactions inside this vibrant biological system. But while consciousness may not be quantum in a technical sense, it is quantum in an existential one. You, as an observer, move through a world structured by quantum rules. You live through experiences shaped by outcomes that were once shimmering possibilities. And though you cannot access other branches of reality, you are part of the branching, not because your mind commands the universe, but because your presence threads into the fabric of events like every piece of matter does. How does this feel? For some, it brings comfort. The idea that reality is wider than we experience, yet our personal thread remains coherent and meaningful. For others, it carries a quiet unease, the sense that the universe is stranger and more layered than our emotions can easily grasp. Either reaction is natural. The universe does not demand that we feel one way or another. It simply is. There's also something soothing in the idea that your life, the particular arc of days and choices that led you here, is not a random accident. Not because it was destined or selected, but because it is your branch, a unique unfolding that holds together with its own quiet integrity. If other versions of you exist in other branches, they are not shadows or competitors. They are simply parallel melodies, never touching yours, never dimming or enhancing what you experience. Decoherence keeps these melodies separate, like songs drifting from different rooms in a large house. You hear only the one you inhabit, and so we return to the heart of the matter. You're not an outsider looking at a strange universe. You are part of it, woven from the same threads that bind particles together, shaped by the same rules that guide stars, connected through the same patterns that underlie all existence. Your consciousness may not orchestrate the quantum world, but it participates in it, experiences it, reflects on it. That reflection is something beautiful, a mind made of matter, contemplating the rules that govern matter, a branch of reality aware of its own unfolding. As you sit with this thought, imagine yourself floating gently on a quiet river. The current moves softly beneath you. You feel the motion, the coolness of the air, the sound of water brushing past the shore. You cannot steer every detail of the river's path, but you can observe it, reflect on it, and find meaning in the experience of drifting. Quantum mechanics is a little like that river, vast, surprising, and gently carrying you along, and consciousness is the quiet awareness of the journey. Whatever the deeper truth may be, whether reality branches in countless directions or remains whole beneath the surface, the life you experience is not an illusion. It is a continuous thread, woven from countless interactions, guided by the subtle rules we've explored tonight. This thread is yours, and it carries you forward, one breath, one moment, one gentle observation at a time. As we reach the final stretch of our journey tonight, imagine yourself stepping out onto a gentle hillside just before dawn. The air is cool, the world is hushed, and the faintest line of light rests along the horizon. It's a moment where everything feels both still and softly expanding, as if the universe itself is taking a slow breath. This is the kind of feeling we carry into our closing session, where we gather the threads we've uncovered and let them settle into something calm and whole. We began with the tiniest actors in the universe, particles that share invisible bonds like distant friends moving in quiet harmony. These connections, these entanglement threads, behave in ways that defy our usual intuitions. They do not weaken with distance. They do not rely on signals or messages. They simply exist, steady, delicate, and real. As we wandered deeper, we saw how even Einstein wrestled with this behavior, calling it spooky, not out of disbelief, but out of his desire for a universe ruled by gentle locality and order. And then we saw how experiment after experiment revealed that entanglement is not a flaw in our understanding. It is part of the very foundation. From there, we drifted into deeper waters. We explored the multiverse ideas, not as dramatic explosions of infinite worlds, but as soft, thoughtful possibilities. We imagined bubble universes rising like small pockets in a cosmic simmer, string landscapes echoing different melodies of existence, and branching histories unfolding like paths in a quiet forest. Through each of these images we asked, what if entanglement is more than just a connection within one world? What if it hints at something broader, a structure that underlies possibilities themselves? We then stepped into the bold imagination of ER/EPR, the idea that entanglement and geometry might reflect each other. Wormholes not as science fiction tunnels, but as mathematical cousins, symbolic stitches in the cloth of spacetime. This didn't give us shortcuts or secret doors, but it gave us a new way to imagine how the universe holds itself together, through patterns of relationship, through invisible seams. From there, we wondered what happens if the universe branches, not as a haunting possibility, but as a delicate unfolding. Each branch carrying its own version of events, each one woven with consistent outcomes shaped by entanglement. We saw how these connections don't let communication slip between branches, but quietly maintain the structure that gives each world its internal coherence. And we asked the soft question, what does entanglement remember? Perhaps the memory is not of events, but of relationships, of how possibilities once intertwined before drifting apart like dancers across separate stages. We then addressed one of the most persistent questions. Could information cross the boundaries between universes? The answer, with what science knows today, is firmly no. Entanglement cannot be used to send messages, not across space, and certainly not across branches. Decoherence acts like a thick velvet curtain, ensuring that each world is private, separate, and self-contained. But even in this separation, the structure of branching suggests a broader harmony, not communication, but coherence, not exchange, but symmetry. With this grounding, we turn toward the quantum frontier, where scientists work not only to understand entanglement, but to build with it. A quantum internet, satellite experiments, delicately entangled mechanical devices, all of these reveal that entanglement is not just a theoretical whisper, but a tool we are learning to shape. As we build the future, each experiment tells us something new about how fragile, resilient, and fundamental entanglement may be. And finally, we brought the story back to ourselves. Consciousness, observation, the human experience of living in a universe threaded with delicate laws. We set aside pseudoscience and instead explored the emotional truth that your life, your experiences, your quiet presence in this moment are shaped by quantum rules. Not because your mind collapses worlds, but because you are part of a reality that unfolds through countless interactions. You inhabit one branch, one path, one coherent and continuous story, your own. Now, as this journey comes to a close, we return to honesty. Some things we know firmly. Entanglement is real. Its effects have been measured countless times. It violates no laws, and it allows no message to travel faster than light. It is one of the deepest and most puzzling features of quantum physics, and some things remain open, shimmering at the edges of knowledge. Whether other universes exist, whether space-time truly emerges from patterns of entanglement, whether the cosmic fabric contains more layers than the one we see, whether the branching structure we explored is a literal truth or a poetic interpretation. Science is built on this balance, between solid ground and open sky, between what we have measured and what we can imagine responsibly. And now, as the first soft rays of dawn rise over the hillside of our journey, Imagine again those invisible threads we've talked about, not as bridges or portals, not as tools for travel or communication, but as quiet reminders that the universe is stitched together in ways we're only beginning to understand. The world you live in is richer, subtler, and more quietly beautiful than it appears at first glance. As you rest with these thoughts, you might ask yourself one final gentle question. If there were another version of you, somewhere in the branching weave of reality, what quiet choice might they be making tonight? Not to compare, not to judge, but simply to appreciate the wonder of possibility. And so, we arrive at our soft landing. Thank you for being part of this quiet exploration. If these journeys help you unwind, relax, or drift towards sleep, you're welcome to subscribe, only if it truly brings you comfort. Before you close your eyes, feel free to share in the comments where you're listening from, and which idea from tonight settled most softly in your mind. As you drift toward rest, imagine yourself held gently by the cosmos, a place threaded with invisible connections, ancient and delicate, whispering softly through the quiet of the night.